Where we left off in our fabrication process was we had a substrate, like so. So here's our P substrate. And over here on the right-hand side somewhere, I'm going to place some end-well material. And as we learned, that end-well material can be used either as the body of a PMOS transistor, or it can be used as a resistor. But when used as a resistor, we actually kind of have to treat it like an RC network. Okay. So the next layer that would be fabricated for an CMOS integrated circuit would be the application of a gate oxide. And our gate oxide layer, as its name implies, is an insulating layer that keeps our gate from physically contacting the body of our transistor. Okay, so this gate oxide layer is typically less than 20 angstroms thick. Okay, how many of you guys know what an angstrom is? Let's start there. Yeah, so it's a 1/10 of a nanometer. So it's a very, very small unit of length. So our gate oxides are typically on the order of 2 nanometers. So we're talking like 5 to 10 atomic layers thick. So it's a very, very, very thin oxide. After that gate oxide is placed, then a layer of polysilicon will be grown or sputtered over the entire wafer. Okay. Not sputtered, chemical vapor deposition. All right. So here we have our polysilicon layer. Now, depending on our process node, we might have access to more than one polysilicon layer. The standard CMOS process has exactly one, but a more advanced CMOS process will probably have 2. And so we're going to talk about both of the layers and physically where they're oriented, and then the reasons for doing it. Okay. So after we apply our polysilicon layer, what would happen is that then we would use a mask to apply photoresist and do a basic photolithography process to define what parts of the polysilicon layer we want to keep to use as our transistor gates and potentially as resistors, and we'll talk about that in a minute. And then we would etch away all of the rest of the polysilicon. All right. So our polysilicon layer deposited through chemical vapor deposition. So it uses silane gas, which I think is SiH4, yeah. And patterned lithography. Polysilicon is effectively chunks of single crystal silicon fused together. Okay. So the reason why we get chunks instead of large regions of single crystal silicon is because we're not starting with a seed that gives us that crystal to grow out of, right? So the silane gas interacts with the oxide layer, little bits of crystal and silicon start growing, but there's nothing to define the boundaries or to effectively really to keep the boundaries going to make a large region of single crystal and silicon. Okay, so let's talk about this polysilicon layer. And actually, let's take the step to have quote unquote patterned it. So I'm going to erase this guy here. I'm going to leave myself two patterned regions of poly. One will be in the middle right here. And let's put the other here. So this is what we have left after patterning of what we would call the poly 1 layer. All right. So that poly 1 layer is very, very close to the body of our NMOS transistor. So it's close to the substrate, and it's physically close to the body of our PMOS transistor, which is that N-well region as well. We might have a second polysilicon layer, which would still be patterned in pink, and we could put it somewhere up here, right? We'll call this guy poly 2. So the second polysilicon layer is physically much further away from our substrate and our N-well. It can absolutely be used as the gate of a transistor, but what is the effect of it being physically oriented further away? So effectively what happens here, right? There's going to be some oxide and so this distance right here will be the oxide thickness for this particular transistor. So what happens is the oxide thickness goes up. Do you think that's going to make it easier or harder to turn the transistor on? Harder, significantly harder. So you effectively have two different voltages that you can use to turn on transistors in a 2 polysilicon process, right? One's going to be a small voltage, typically on the order of 0.6 to 0.7 volts for the poly that's very, very physically close to the substrate. And it could be as high as 1.5 to 2 volts for the poly that's further away because of that very, very large oxide thickness. Okay, so it gives you a second transistor technology to use within the same process node. So if this polysilicon is undoped, and we'll talk about that in a minute, and I'm talking about either layer here, but technically speaking, it would usually be that second poly layer. So I'll say if this poly 2 is not doped, it has a resistance R square. I'm going to call this HZ of approximately 1 kiloohm per square. All right. So these would be called high Z or high res poly 2 resistors. Okay. So we can use the polysilicon layers to create resistors as well. So we spent a long time talking about N-well resistors having roughly a sheet resistance of 800 ohms per square in a C5 process. And now we have access to a different way to make resistors, having a sheet resistance of only 1 kiloohm per square in that same process. So the amount of resistance that is increased by using these high res poly layers isn't really that much more, right? It's only 25% higher than what the N-well itself gave us. And it's because the N-well is behaving like effectively single crystalline silicon over large regions. And the high res poly is single crystalline silicon over short regions. And so that mishmash of crystallography is what's giving it that increased amount of resistance. But other than that, there's really no difference between the two. So why might the inclusion of a high res poly layer be a good thing? Performance wise, it's really not that much more resistant. Any thoughts? So there are design rules and all that kind of stuff, but the spacing is, let's say that the spacing is roughly the same. Okay. I would argue that it's harder to make. So it's going to have something to do with some capacitance. Okay. So you're going to have a conductive layer physically separated from your conductive substrate, and the distance between those two conductors is larger. Okay. So you're going to have less capacitance, but you're overlooking something kind of super obvious here. If this poly isn't sitting in the substrate, can it form part of a PN junction? No. That's why high res poly is used for resistors. So in an N-well process, and I ask you guys this in your homework assignment that I put up over this weekend, what happens when an N-well resistor and you apply a voltage drop across that resistor so that the potential at one end of the N-well resistor is greater than the potential at the other end of the N-well resistor? What's going to happen to the space charge layer as that potential gradient exists? It's going to change shape across the entirety of the resistor, right? So the space charge layer at the low potential side or no potential difference side, so the 0 volt side, is going to be at an unbiased capacitance width. And on the biased side, the space charge layer is going to be a lot larger, right? Which means the capacitance over the length of the resistor changes. And the resistance over the length of the resistor also changes because the thickness is no longer uniform, right? So the thickness is going to have a potential gradient as well. And since that thickness has something to do with the resistance, effectively, you're going to wind up messing around with both of the R and the C value, and they're going to be different at different points in the resistor, in the N-well resistor. For the poly 2 resistor, you don't have to worry about that whatsoever because there is no PN junction formed. So it's a uniform conductor through and through. So, like I said, while I would argue that a process involving this second polysilicon layer is actually significantly more expensive than without it, the benefits are pretty huge, especially for analog systems where resistor values like actually matter, right? The tolerances and all that kind of stuff need to be tighter. So these high-res poly 2 resistors are formed by not doping the poly 2. You may be saying to yourself, well, that's pretty easy, you just don't dope it. How that happens is that oxide is grown, and then during a subsequent doping process, you just make sure that you don't etch away that particular oxide. And so that's going to bring me to what are called the active layers, all right? And we're going to talk about how the polysilicon layer itself acts as a physical mask in the formation of the transistor, okay? So after let me copy this picture here. I'm just going to take this part of it, edit, copy. Edit, paste. All right, that seems good. Let me switch to my pen thing here. I'm going to draw a top-down view as well, because I think that'll help us understand what I'm about to say. All right. So from a top-down view, we might have something that looks like this. So this is obviously our side view. Small portion of the wafer, but everything in black here is our substrate. Then we have our end well region right here. Now we have our poly sitting on top of our gate oxide, sitting on top of that end well, physically located on top, right? And similarly, if we etched away all of the silicon dioxide, or our gate oxide, except directly underneath our polysilicon layers, we would have something that looks like this from the top-down view and from the side view, okay? So now what we're going to be doing is we're going to be talking about the formation of the drain and the source regions, as well as the body connection region, okay? So let's say specifically that we were doing a P active region, all right? So our mask for our P active region, which I think I did in orange, would look something like this. And then On this other side, I'm going to put a little bit right here. Okay. And to help you kind of visualize what's happening here, I'm going to put a dashed line through this, and then a dashed line where things would line up. On our wafer as well. So this little guy right here isn't actually on top of anything else, right? It's not like we would be sliding this mask over the top of our wafer and lining things up along that dashed line as kind of a registration type thing, right? So this guy right here that I put the arrow at, that doesn't really line up with anything except a region out on the wafer. So it's just going to convert some small portion of the substrate to be p-type or heavily doped p-type, right? Very, very heavily doped p-type. So I'm going to draw that guy up here. As lined up as I can make it. And so we have this extraordinarily heavily doped, so I'm going to call this part right here P+ region, sitting inside of our p-type substrate. All right. What that's going to allow us to do using subsequent processing layers is to electrically bias our substrate to a specific voltage level using a metal semiconductor junction known as an ohmic contact, okay? So when we have metal semiconductor junctions, we have two options, all right? One option is forming an ohmic contact, and that's exactly what it sounds like. It just allows electricity to pass through very easily. And then the other option is what's called the Schottky diode. A Schottky diode is a metal semiconductor junction. So it's like a PN junction, except that instead of having semiconductor material on both sides, one side is metal. And so it's still a one-way diode where there's effectively an infinite amount of electrons on one side of the junction. Having a Schottky diode here would be a bad thing because we're not trying to limit current flow in any way, shape, or form, right? A diode is a one-way valve for current to flow through. We want all of our current to effectively be able to flow to ground, which is what we're doing here with this guy, right? So the Schottky diode would prevent that from happening, and we would have effectively stray potentials throughout our chip. This is the way that we get to bias our substrate to where pretty much the entirety of the substrate will be at a 0-volt potential or a big ground plane. When I put this other mask on top, up here, of this region, what's going to happen is that this entire region that I've boxed in orange is going to be bombarded with acceptor ions, right? So it's going to be bombarded with acceptor ions. And what we will see physically happen from the side view is that our source and drain are formed on either side of the polysilicon layer, but our polysilicon layer also gets doped significantly. so much so that its sheet resistance changes from roughly 1,000 ohms per square to like 25 ohms per square. Okay, so it is a huge amount of dopants that are going in there. This is what's called a self-aligned gate fabrication step. So the gate acts as a mask. All right, and what it lets us do, or effectively what it makes sure that happens, is that this entire region gets bombarded so that there's no way. So if we defined the source and the drain of our PMOS transistor, right? This is P plus, this is P plus, so it's going to be a PNP or a PMOS transistor here. If we defined those regions first, and then we pattern the polysilicon gate on top, there's a chance that we could misalign it and our transistor would never be able to turn on, because it physically wouldn't be able to cause a channel to form underneath it. This other way around, where we put the polysilicon down first and then use that as a physical mask, make sure that can never happen, because we bombard that entire region. So there's literally no way the gate is misaligned to the source and the drain regions, okay? So the invention of this technique occurred in, I want to say, the late 70s, early 80s. So before this point, actually, gates weren't made from polysilicon at all. They were made from aluminum, which is why they're called MOSFETs. It's metal oxide semiconductor. Well, now it's really semiconductor oxide semiconductor. We just dope that first semiconductor region so much that it behaves as if it were metal, or pretty close, right? Sheet resistance of this highly doped poly is on the order of 20 to 25 ohms per square. The sheet resistance of metal is on the order of 1 ohm per square, maybe a little bit less, maybe a little bit more, just depending on a couple of factors and which metal. So it's the best happy medium that we can get, and it also gives us the highest possible yield that we could ask for, okay? So this guy right here, this orange layer, is technically two masks. One is called the active and one is called the select, okay? So if you look in your Moses design rules, there'll be different rules for active and select, but they're very, very integrated. Really, the only design rule for the select is that it has to overlap the active region by a small amount. In some VLSI programs like electric, it's all built together into one layer, and that's how I'm going to treat it here. But they technically have two different functions. The select layer tells the operator where to bombard with those acceptor ions. The active region tells where to cut a hole in the field oxide to allow that bombardment to happen. So they're so closely related. Again, most things treat them as if it's really just one mask. Like most design programs treat it as if it's one mask. So this is, we're going to call active and selective. Okay. All right, so after we did our P plus implants here, forming the source and the drain of our PMOS transistor and a portion of the body connection for our NMOS transistor, what do you think comes next? We need to do the exact same thing for the NMOS, right? So we need to form the source and the drain of the NMOS, and we need to form the body connection for the PMOS. So we do the exact same thing with a very similar mask. So let's call this P active and select. So now we'll do an N active and select. I feel like I did that with green earlier. And so it's going to look like almost exactly the same mask. Oops. And we'll line this guy up over here. Put our dashed line through the middle. And what then occurs, we line up our mask in this region, and then in this region, which winds up forming an N plus region here, an N plus region here, and N plus region here. And it looks like I forgot to draw the P plus region for the last thing, so I'll tuck that in right here. And we now have a fully realized NMOS transistor and a fully realized PMOS transistor. We just now effectively don't have any way to get signals onto or off of these guys because we haven't made metallic connections. All right. The resistance of these implants is approximately 125 ohms for the P-type implant. And it's approximately 100 ohms per square. Sorry, I forgot to put the ohm symbol here. For the N-type implants. So we have yet another thing that we can use for resistors, but these are typically used, so you would make resistors out of these implants when you want very small value resistors, right? Oh, I say very small value, like you wouldn't do kilo ohm scale resistors with these because it would take up too much space. That's what the N-well and or the high res poly layers would be for. But if you need a 50 ohm resistor in your circuit, you wouldn't want to use metal because it would take too much metal to hit that resistance. And you wouldn't want to, I don't know that you could physically do it with poly or N-well, and make sure, you'd have to make sure that the current flows through it in a oblong direction or something like that. So this is how you get those kind of intermediate values, so not on the order of ohms, but not up to kilo ohms yet either. All right. So talked about active and select regions. We've talked about our polysilicon regions. So now let's talk about contacts and vias, right? That'd be the next thing that we would deal with. So this will be part of our metal layers. And depending on the process, may literally be part of an actual metal layer that's deposited, or it could be something else. And so what I mean by that is depending on your technology node. Okay, so let me draw where we're at. So let's say that we have our substrate. like so. We have deposited our N well region. We have here is P plus, here is P plus, here's N plus, so that's our PMOS transistor. Then over on the other side, give myself enough room to do this. N plus, N plus. I'm going to put P plus on this side now. We have our polysilicon layers made, acting as our gates. And we have grown an oxide region over this whole thing. So these poly regions right here have been doped ostensibly, okay? So this whole thing is covered with a layer of insulating material that is our field oxide, or some combination of field oxide and gate oxide. They're the exact same thing, just the gate oxide is what's physically separating the poly from touching our substrates here, okay? We want to get chips, or excuse me, we want to get signals onto and off of our chip, which means we're going to have to run wires effectively. So we would have to cut out regions of our oxide layer. Anywhere we want to make electrical contact. So I'm just cutting out those little regions here. And technically, we would need to be cutting out regions for the poly as well. I'm not going to draw that right now. Okay. So we have something that looks like this, where we've cut away regions of our oxide so that we can ostensibly figure out how to contact that P plus region that forms the body connection for our NMOS transistor, our source and our drain for our NMOS transistor. And then we have our source and our drain for our PMOS transistor, and then the body connection for the PMOS transistor. So depending on the process, this can be approached in one of two ways, all right? The old school way is that you just sputter aluminum over literally everything, okay? Like literally over the entire surface of the wafer, and then you etch away what you don't need. The more modern process is the implantation of tungsten plugs, okay? So our contact or via layer is going to be implanting these tungsten plugs in these specific regions, all right? So this is our contact layer. Tungsten has the symbol W. Tungsten plugs. And then immediately after that, we would deposit our metal 1 layer. I believe metal 1 is usually aluminum, or it's an aluminum alloy. Metal 2 is, so it's like you start off with aluminum, and then as you get further and further up, like physically up away from the chip itself, it starts using more and more copper. All right. So these contact layers are critically important. Okay, they have a relatively low resistance, 10 ohms. I'm not saying it's 10 ohms per square. So these contacts, let me, I guess, put it down here. Rules for contacts. They have to be 2 lambda by 2 lambda. And so they, because of this, they each represent a resistance of approximately 10 ohms. Edit, no. I want to open up my original. Thomas, I apologize. Zoom crapped out on me there for a second. Let me reshare my screen. All right, so I was talking about this. This is our inverter layout from our first real lecture. And I was saying that if we actually laid out a circuit like this, it would be a very bad idea because we only have a single point of contact between our metal layers and our implants and all that kind of good stuff. So if any single one of those contacts failed, we could no longer actually apply signals to our circuit. So instead, we'd likely do it with arrays of contacts. And you may have noticed, gosh, my nose is itching so much, that when you guys made your transistors in electric, it automatically put those arrays of contacts in place for you. The larger you made your transistor, the more contacts it added. So electric largely takes care of this for you, okay? It tries to add in fail safes and all that kind of good stuff like that as is needed, all right? So let me see what, okay. So we have our contact layer with our rules. They have to be 2 lambda by 2 lambda, like literally anything. If you try to do anything else, you'll get errors. And then we deposited our metal layer on top, okay? So all of our CMOS processes are gonna have at least 1 metal layer. The process that we are going to design to, the on semiconductor C5 process, has 3 metal layers. Having additional metal layers is very, very helpful because it allows us to use multiple layers to route how signals are going to go and all that kind of stuff, right? The reason why that's important is, let's say that we had a metal run like this, just a simple wire, okay? And then we tried to deposit a run that went transverse to it. On a single metal layer, these guys just form one big T-shaped metal connection. Whereas if we have access to multiple metal layers, the first one in blue, and then the next one, gosh, don't think I have a color for this one yet. Let's do not crazy bright pink, because that's what I use for poly. So this other pink. Hopefully this isn't going to get too confusing. This pink run is now physically separated from the blue metal run by a reasonably thick layer of insulation. Okay. All right. So having multiple metal layers really helps us out with routing signals around chips. When we get to, like, if you're getting to the order of making your own, kind of microprocessor or processor chip, 10 to 15 metal layers is not unreasonable. Okay. There is one specific portion of the metal layer that is the only part of a CMOS process that does not have a lambda-based or scalable design rule. That's a bonding pad. All right, so let's start talking about specifics of the metal layers. All right, so our topmost metal layer will be, in our process, metal 3, which I believe in electric looks kind of gold colored. All right. So to get signal on or off requires the use of a bonding pad. All right. So if we had so the rules for simple metal runs or wires and all that kind of stuff, I think they need to be at least 4 lambda wide, and then their length is whatever their length needs to be. So for a 300 nanometer lambda, what physical dimension is 4 lambda? So 4 times 300 nanometers is 1.2 microns, right? So if we were trying to solder to a 1.2 micron square section of metal, that'd be practically impossible, right? Couldn't do it. That's where bonding pads comes in. If for us as macro scale people to be able to interact with things at the micro scale, we need some sort of interface. And that's what these bond pads are. All right. So a bonding pad requires a 60 micron by 60 micron minimum opening in what's called the passivation or over glass layer. Okay. All the passivation or over glass layer is, it's an extra insulator layer on top of your chip that physically holds things down. Because if you had metal directly exposed, it could corrode or flake off. So this is literally just another, it's literally heat treated silicon dioxide so that it forms effectively glass that just holds everything down. Nothing remotely fancier than that, okay? We have to have a minimum of 60 micron by 60 micron opening for the computers to be able to solder to these things to make our leads go out. Okay, so that's why we couldn't do a 60 micron by 60 micron physically either. But so there's a 60 micron by 60 micron bonding pad, or there's 8 of them in the MUA 741 chips that we're going to be using in the lab and all that kind of stuff. Teeny tiny wires that go out from them that connect to the actual posts on the dual inline chip package and all that kind of stuff. As I said, this is the only design rule that does not scale. All right. So this is rule 10.1. That does not look remotely like 10.1. I guess it does now. All right, in your SCMOS design rules. Then there is a rule that the pad metal overlap passivation is 6 microns. So that means the hole you cut in the over glass layer to solder to is slightly smaller than the bonding pad itself. All right. And the reason for that is misalignments. We want to be able to hold the whole bonding pad down. So effectively, what we have is color. A large (72) micron by 72 micron square. And then the overglass layer, we get a hole out that is 60 microns by 60 microns. It allows us to actually physically connect a wire to that to lead off of like a conventional wire, not just a strip of patterned metal. Okay. There can also be probe locations. So if this is a physical space on the chip that you want to be able to test. So like, I know not all of you guys work in the IFM, but have you, the 3 of you that work in the IFM, have you ever seen like the micro manipulator tools and all that kind of stuff? So a micro manipulator tool is effectively this little box that can move in the X, Y, and Z directions that steps down mechanical rotation of these gears to micron level movements of a needle-like probe so that you can look at things under the microscope and actually physically target a specific area on something you're making. So those holes need to be 20 micron by 20 micron. So that's the minimum size there. But the overwhelming majority of you will never actually have to physically go do that, but I wanted to mention it for the few of you that literally might, okay? What happens if you forget the passivation openings in your design? Can't get to the chip. You've got a layer of glass over the region that you need to access. Right? It's literally that simple. Okay, so you have to always remember when you're doing your bonding pads and all that kind of stuff, designing them. The 72 micron by 72 micron is the absolute minimum. Chances are they're going to be larger than that, just depending on how many you need and the size, space, and all that kind of stuff that you have. I would argue that you want to make them larger than the minimum size if at all possible, because that is your access to the chip from our scale of stuff, okay? So what things kind of look like from a side view, I think this will be is we would have an overglass layer holding down a section of bonding pad. So this is our overglass. Something I want color. Here's our metal 3 layer. A chunk of insulation. And then we would have, I think this is the color I used for metal 2. More insulation. Here's a section, metal 1. And then metal 1 through our contacts gives us access to our actual source, drain, body connection, and all that kind of good stuff. So how do we get from metal 3 to metal 2, metal 2 to metal 1? It's literally the exact same thing as a contact, except it's got a different name. It's called a via. Okay, exact same rules, exact same material, all that stuff. I have no idea why they give it a different name, but it's a via instead of a contact. So we would see a tungsten plug that is 2 by 2 that would allow us to connect down through our metal layers. So this would be via 2. And this would be via 1. All right. You cannot connect metal layer 1 directly to metal layer 3. you have to go through metal layer 2 as well. So when you're routing stuff in your designs, be aware of that. Like you literally won't even be given the option to do it. So like what I like to do to save space is stack my contacts and all that kind of stuff on top of each other so that it's effectively a run of metal in the plane of the substrate and then a 90-degree right turn up to hit the metal layer I want to go to and then out. But it has to go through metal 1 to via 1 to metal 2 to via 2 to metal 3 and then towards a bonding pad, right? You can use metal 3 as a regular metal layer in addition to using it as a bonding pad and all that kind of stuff as well. So you're not restricted to only using it for bonding pad, but that's where your bonding pad is going to be. All right, I think that's enough out of me for today because my nose is driving me absolute crazy and I want to go scratch the bejesus out of it. So I will see you guys on Wednesday where we will get into a lot of math dealing with the metal layers and all that kind of good stuff. I have put our class meeting videos for class meeting 1, 2, and 3 up on the Moodle page. I will have last Friday's meeting up hopefully later today or early tomorrow morning, and potentially this meeting up tomorrow morning as well, so that you can use all that stuff for your homework set, which is due this upcoming Friday. All right, catch you guys later.